We are presented with a square and an equilateral triangle, positioned in a very specific way. Our goal is to determine the side length of the square. The equilateral triangle has a side length of 20 units. It shares one vertex with the square, while its other two vertices touch the adjacent sides of the square. Let's label the vertices of the square as A, B, C, and D. The shared vertex A is the anchor point for our entire construction. The triangle's other two vertices, Q and R, rest on the square's sides. This constraint is what makes the problem interesting and solvable. The crucial piece of information is the triangle's side length, which is 20 units. All three sides have this length. Because the triangle is equilateral, all of its internal angles are 60 degrees. This angle at vertex A is particularly important. Our unknown, the value we are searching for, is the side length of the square. We will label this quantity S. The arrangement of these shapes creates two right triangles in the corners of the square. These two triangles hold the key to the solution. Their right angles come directly from the corners of the square. Let's mark them to be clear. To analyze these triangles, let's define an angle. We'll call the angle in the bottom triangle theta. This is our main variable. Now, let's focus on the corner A. The corner of the square is by definition a perfect 90 degrees. The equilateral triangle's 60-degree angle occupies the middle of this 90-degree corner. What does this tell us about the remaining angles? It means the two small angles, our theta and the one in the top triangle, must together sum to 30 degrees. Therefore, if our first angle is theta, the angle in the other corner triangle must be 30 degrees minus theta. This insight is the heart of the solution. With our geometric understanding complete, we are now ready to construct the mathematical solution. Now, let's translate this geometry into the language of trigonometry to find the value of S. Let's begin with the bottom right triangle. We can relate the side S, the hypotenuse, and the angle theta using the cosine function. Cosine is the ratio of the adjacent side to the hypotenuse. In this triangle, that means cosine of theta equals S divided by 20. Next, we examine the top right triangle. It has the same structure with an adjacent side S and a hypotenuse of 20. Here the angle is 30 degrees minus theta, but its cosine, the ratio of the adjacent side S to the hypotenuse 20, is the same. And this is the breakthrough. Since both of these cosine expressions are equal to S over 20, they must be equal to each other. For acute angles like these, if their cosines are equal, the angles themselves must be equal. This reveals the problem's hidden symmetry. Solving this simple equation by adding theta to both sides, we find that 2 theta equals 30 degrees. Therefore, theta is exactly 15 degrees. Now that the angle is known, finding S is straightforward. We substitute 15 degrees back into our first equation. S equals 20 times the cosine of 15 degrees. But what is the cosine of 15 degrees? We can find its exact value by expressing 15 degrees as a difference of two more familiar angles. We can write 15 degrees as 45 degrees minus 30 degrees. This form allows us to use the cosine angle subtraction identity. The identity expands this to cosine of 45 times cosine of 30 plus sine of 45 times sine of 30. We know the exact values for these standard angles. Substituting them in gives us the square root of 2 over 2 times the square root of 3 over 2, plus the square root of 2 over 2 times 1/2. Multiplying and then combining the terms gives us a single beautiful fraction, the square root of 6 plus the square root of 2, all divided by 4. Finally, we substitute this exact value for cosine of 15 degrees back into our equation for S. The 20 in the numerator and the 4 in the denominator simplify to 5, leaving us with our final answer. The side length of the square is 5 times the quantity square root of 6 plus square root of 2. A precise answer derived from uncovering the deep symmetry of the problem.